So welcome everyone after the short break. We resume for the last two talks for this session. The first speaker is Professor Pierre Philippe Cortet from CNRS and University Paris-Saclay. He's going to speak about three-dimensionality of the triadic resonance instability of a plane inertial wave. You can get started when you're ready.
Okay, thank you very much. So yes, I will discuss the problem of the fundamental problem of the triadic resonance instability of a plane inertial wave. So this is both experimental and theoretical work that has been done in my team. With Daniel Mora, Eduardo Monsalve, and Maxime Brunet, and in collaboration with Thierry Dauxois from ENS de Lyon. So obviously the general framework of this work is hydrodynamics under rotation, which is described by the Navier-Stokes equation in a rotating frame. So in which on the right side, you notably have the Coriolis force minus 2 omega times u, where omega is the vector rotation rate of the system. So as you know, in order to know in which regime this equation operates, you can introduce two non-dimensional numbers, the very classical Reynolds number, and second, the Rossby number, which compares the intensity of the nonlinear term of the equation to the intensity of the Coriolis force. If you take the linear and inviscid limit of this equation, you, as we already heard several times, you get an equation of propagation of internal waves, which are called the inertial waves. Their dispersion relation is written here. It actually relates the ratio of the wave angular frequency sigma to 2 times omega, the rotation rate, to a given specific angle theta. Which is both the angle that makes the wave beams with respect to the horizontal, and also the angle that makes the wave vector with respect to the rotation axis. Okay, so so these waves, I cannot. Okay, so these waves share a lot of features with internal gravity wave in stratified fluids. They have a group and a phase velocities that are normal to each other, a wavelength which is independent from the wave frequency, but they also are quite different for other aspects. The most important one being that the motion of the fluid particle inside the wave is three-dimensional. It consists actually in an anticyclonic circular translation in the planes tilted of the angle theta, the planes of constant phase. So you have an oscillation which is here out of plane, perpendicular to the screen. So what you are seeing here is a plane inertial wave that has been that is measured experimentally in a vertical plane of the rotating frame. Okay, so another important remark about this wave is that if you consider a plane inertial wave at an angular frequency sigma 0 and a wave vector k0, it is still an exact solution of the fully nonlinear and fully viscous equation, but and it is not something new, it is an unstable solution with respect to the triadic resonance instability. Okay, and this instability actually drains the energy from the primary wave towards a couple of subharmonic waves at frequencies sigma 1 and sigma 2, which are lower than the forcing frequency sigma 0. And the three waves are in triadic resonance, which means the sum of their three frequencies and the sum of their three wave vectors is equal to 0. Okay, so what is quite comfortable with this instability is that we have an exact theoretical framework to describe this triadic interaction between three plane inertial wave. This corresponds to this equation. I don't have time to get into the details. It comes from the helical mode decomposition of the Navier-Stokes equation. And you can, from this equation, you can predict what happens at the early times of the instability, which is an exponential growth of the subharmonic waves at a rate gamma, which writes like this. and which involves in particular the two triadic interaction coefficients C1 and C2, of which I don't give the formula because I don't have time, but this is an exact formula for the growth rate. Okay, so in the following, we will analyze this and we will assume that the primary wave propagates in a specific vertical plane, which is the vertical plane XZ, which means, so this without loss of any generality, obviously. And this means we consider a wave which is invariant in the horizontal Y direction, which is the direction normal to the screen. And it corresponds to a KY component of the wave vector of the primary wave, which is equal to 0. But we will let the possibility that the two secondary waves produced by the instability propagate in other vertical planes than the vertical plane XZ in which the primary wave propagates. Okay, and then so first we can analyze the inviscid case from the previous equation, and we can get, after some analytical calculation, we can get to this equation, which gives you a simple formula for the growth rate of the instability gamma normalized by the nonlinear frequency of the primary wave. And this formula depends only on the angle alpha 2, which is the angle which is opposite to the K2 wave vector in the closed triangle formed by the three wave vectors of the three waves involved in the resonant triad. What you can do further is to maximize this growth rate with respect to the angle alpha 2 in order to find which is the couple of subharmonic wave that maximizes the instability growth rate, which is something very classical to do. And the result is that the secondary waves propagate in very different vertical planes compared to the primary wave vertical plane. What you can see here is a view from the top of the three wave vectors. And actually, we define this angle phi between the vertical plane of propagation of the primary wave and the vertical plane of propagation of the secondary waves. And theoretically, we predict that it will range from 60 degrees to 90 degrees for a primary wave non-dimensional frequency sigma 0 star going from 0 to 1. So this is due to this equation. And all these results are completely exact. And it actually predicts that the triadic resonance instability of a plane inertial wave is a very strongly three-dimensional process. Okay, and so in the general viscous case, we cannot do the mathematics analytically, but we can simply compute numerically the values of the growth rate and maximize it with respect to the secondary waves. And we also find an equivalent result, which is that the secondary waves propagate in very different planes compared to the primary wave. Okay, so in the second time, we wanted to check, to observe this result experimentally. So we have realized this experiment in which we force plane inertial wave with a wave maker in a rotating water tank, which is quite large. So I don't have time to describe in detail the wave maker, but an important specificity of this wave maker is that in the horizontal Y direction in which the forced primary wave is supposed to be invariant, the wave maker is quite large. It is of 50 centimeter. It is 50 centimeter large, which corresponds to more than 7 wavelengths of the primary wave. We can now look at a few experimental results. So first, I show you here the temporal energy spectrum of the velocity field as a function of the non-dimensionalized frequency sigma star. So what you can see here first is a very dominant energetic peak at the frequency of the forcing here, which corresponds to the primary wave. And then if you consider a different spectrum like this for different forcing amplitude, you can see that above a threshold, you see the emergence of two subharmonic bumps here with a maximum in energy at frequency sigma 1 and sigma 2. These two bumps are perfectly symmetric with respect to half the forcing frequency sigma 0, which corresponds to triadic resonance in time of the three modes. So we already have 3 temporally resonant modes. And what we can do now is to look at the spatial structures corresponding to these 3 frequencies, sigma 1, sigma 2, and sigma 0. This is what is done in this slide, in which we have realized Fourier filtering around each of these frequencies. On the left here, you can see the primary wave at the forcing frequency sigma 0, which is a nice plane inertial wave. In the middle, you can see the velocity field of the mode at frequency sigma 1 star equal to 0.28. And on the right, you can see the velocity field of the mode at frequency sigma 2 star equal to 0.56, these 3 modes being in temporal resonance. What we have done next is that we have identified a region where the 3 waves are present. We highlighted this region with the dashed square here. And in this region, we have computed from the velocity field the wave vector, the experimental wave vector in the vertical plane of measurement. And we have realized that for the 2 subharmonic waves at frequency sigma 1 and sigma 2, the direction of this wave vector K1 and K2 with respect to the vertical was not at all in agreement with the dispersion relation. And so the natural interpretation for this result is that these 2 subharmonic waves propagate in different vertical planes and then compared to the primary vertical plane XZ of the primary wave. And what we can do is use the dispersion relation in order to compute the out of plane component KY in the horizontal direction that is out of plane of the wave vector from the dispersion relation. So this is this equation, which is simply an inversion of the dispersion relation, such that we can access the 3 components of the wave vector of the subharmonic waves. And now we can compare this experimental measurement to the theory. This is what is done in this plot. So in this figure, this is a very famous figure. It represents with the different curves, the dashed curve, the continuous curve, and the dashed dotted curve. It represents all the locations of the tip of the K1 wave vector in the plane Kx1, Kz1 that are predicted by the triadic resonance condition. So this plot has been published in several papers about triadic resonance instability in the past. Okay, on this plot we add the triad of experimentally measured wave vector, which are these 3 arrows. You can see first that this triad forms a nearly closed triangle, which means indeed the 3 modes that we observe are spatially resonant in addition to be temporally resonant. But what you can see is that the tip of the K1 wave vector, which is blue, does not fall at all onto one of the resonance curve. This is actually due to the fact the secondary waves propagate not in the primary wave vertical plane, but now we can look at the same figure, but actually the resonance curves are just cuts of resonance surfaces in the 3-dimensional space of the K1 wave vector. And in this plot on the right, what we show is 2 resonance curves in another cut of the space, which corresponds to the KY1 component of the K1 wave vector equal to its experimental value. And in this plane, you can see that the tip of the K1 wave vector falls very well on one of the resonance curves. Okay, so here the conclusion is that we observe a triad of modes which are temporally resonant, spatially resonant, and with the subharmonic waves propagating in different vertical planes compared to the primary vertical plane. We can now look at another comparison between experiment and theory. In this plot, we report the map of gamma, the growth rate that is predicted theoretically. In this time in the horizontal plane, Kx1, Ky1, and you can see something what I said earlier, which is that the maximum growth rate is found here. It is highlighted by the black dot at a location which is not at all in the ky1 equal to 0 vertical plane. So indeed, the theory predicts a strongly three-dimensional instability. And we have reported on this figure the experimentally measured thread of wave vectors. And you can see that the tip of the K1 wave vector, which is represented with the blue arrow here, is found quite close to the location of the maximum of the theoretical growth rate. It is actually within a region where the theoretical growth rate is larger than 98% of its maximum. Okay, so I will conclude. In this work, which regards a very fundamental problem, which is very not new, we have shown, and this is new for the first time, that the triadic resonance instability of a plane inertial wave is a three-dimensional process, which changes the orientation in the horizontal plane of the propagation of the energy from the primary wave to the secondary waves. And these theoretical results are completely exact. In a second time, we have confirmed experimentally this result with observation that are in a quite nice quantitative, near quantitative agreement with the theory. All these results are relatively important regarding the wave turbulence regime that can emerge in rotating turbulence, because you understand that this strong three-dimensionality of the triadic resonance interaction between three waves, it will contribute to redistribute very efficiently the energy in the horizontal plane, and it will build progressively a statistical axisymmetry of turbulent flow in the wave turbulence regime. And this is very important because when people are doing the theory of wave turbulence, they most of the time assume this statistical axisymmetry. So okay, maybe I will conclude with the last point, which is what about this such three-dimensionality of the triadic resonance instability in the case of internal gravity wave in stratified fluid? For this system, this is an open question, at least a partially open question. Okay, and so I thank you for your attention, and I can take some questions.
So we have time for some questions.
Okay, maybe can I ask?
Yes, please. Go ahead.
Okay. Thank you very much for the talk. And the question is whether in the experiment, the wave maker, it occupied all the third transversal length of the experiment, or it was a part of it. The question is because if it is three-dimensional, then the lateral boundary conditions may influence the development of instability and the waves themselves. Yes, here it is.
Yes, yes. So the answer is that the wave maker does not occupy the whole dimension y. It is 50 centimeter large in this direction, and the tank was 80 centimeter large. So you have 15 centimeter here and here. So obviously you can have, we are not perfectly invariant in this direction y, and but as long as you don't look at the propagation of waves too far from the wave maker, you can, in the middle of the wave beam, we can assume that the three-dimensional effects due to the boundaries and etc. are not that important, but surely at some point they will be. Maybe the right answer is that what we measure experimentally is in very nice agreement with the perfect the plane wave theory. So this is my argument to say that everything is working here.
Okay, thank you.
Thank you.
Are there any other questions?
I have a question.
Yes.
Hi, Pierre. I have a question regarding your what's the K1 or KX1 KZ1 plane that you drew. I was not sure. It's not the usual way of drawing, but I'm sure you checked that. But normally the K1 starts at the origin, and then the tip ends.
Yes, yes, but here this is the case. You see that the K1 origin is on 0, 0 here.
Okay, and
but you can see what do you see here is the projection in the vertical plane XZ of the K1 wave vector.
Okay.
What
I mean, or maybe it's just a question of definition, but the K0 also should start at the K0 is the one that actually defines the other all the curves.
Yes. So this is the red arrow here.
Your K0 ends at the origin, but I think it's just a question of defining.
This is okay. This is a matter of convention about the sign of the frequencies in our framework, theoretical framework. We allow frequencies to be negative, in which case the real wave vector is reversed. Compared to, because minus sigma minus k wave is identical to sigma k wave.
No, it's fine. It's also that since your axes are not symmetric, when I saw it the first time, I thought it was not at the origin, but because the origin is not at the center of the square. That's what I mean. Okay.
Maybe to complement, I think I have it here. I just can show you the 3D. This is the theoretical 3D resonance surface. In pink here, and that, of which we are looking at different cuts.
Okay, thanks.
There's one more question in the chat and there's a raised hand. So I'll just read the chat question first from Abhishek Ranjan. Is the frequency at which you force in the wave number important at all?
Oh, I don't know. I mean, experimentally, we checked only one frequency, so I cannot tell more about the experiment. From the theory, we can see, I don't remember very well, maybe I have some plots, no, I don't have plot here as a function of the frequency, but I think at small frequency, the three-dimensionality disappears below a given frequency, but that is quite low. This is due to the fact below a given frequency, the mode that is the most unstable changes. It is not the minus, plus, minus mode. I'm speaking about the helicities of the three waves. In changes of mode, the most unstable one becomes the minus, minus, minus mode. And for this minus, minus, minus mode, the instability is no more 3D, but it happens only at very small frequencies for very horizontal waves. So it's a bit marginal. And this mode actually is not, this is not possible to see it at all in experiments because it produces long wavelength secondary waves. So in order to observe it in experiment, you will have to produce a primary wave beam experimentally, which contains 20 wavelengths or something like this, not to be submitted to finite size effects. I don't know if I answer well.
Sylvain, is it okay if you take the question after the next talk?
Yes, it's okay.
Yeah, so we'll just finish one more talk and then we'll have time for more questions. So thank you once again, Professor Cortet, for this talk.